All right, hello. Welcome everyone to the 2025 October monthly puzzle showcase. So I'll be going through let's see, I think 10 submissions to the puzzle. Um, it, so I also, I both was the author, host, and a participant in this puzzle. So I think it's been very fun seeing what everyone's come up with. But all right, let's get started with Grease Fire's solution. I believe this is Teddy on Discord. Um, so their solution is, I think, kind of the most reasonable approach to this puzzle. So there, you've got you take the input, sort out carbon and nitrogen, and then use like a buffer between the two reactors so that you can very easily uh, make the output. They also double pump the solution or the first reactor in order to make it faster. Yeah, kind of nice. And the second reactor is a very straightforward way to make cyanide. Or yeah, I'll just refer to it as cyanide. So I think, yeah, this is, I think, a great starting point for this puzzle. You've got carbon and oh, I guess maybe I should talk a little bit about the puzzle. You've got a 50-50 split of carbon and nitrogen with one atom coming every cycle, and you're trying to make cyanide, and the metric to optimize for is cycles. There's a tiebreaker for symbols, but that didn't end up mattering here. Um, so people will be trying to make things as fast as possible. But yeah, this is kind of a good, I think, a good benchmark. And Teddy, thank you for. I know we had, I think, two people who I haven't seen submit to any of these things before, and Teddy, I believe you were one of them. So thank you for also submitting. It's not, yeah. I'm glad to see some people who newer people joining this scene. But all right, I'll also quickly note some things for instructive things that you can do to sort of speed this up. For instance, all of this can be moved down a little bit and to the right, and this saves some cycles by shortening the loop. But oh, let me actually run it to completion on the normal thing. So this gives us a starting benchmark of 17,000 cycles. But yeah, so you can move that down, for instance. That's kind of, there's some other minor things you can do if you want to. For instance, you can move this to here, and that also decreases the cycle length in the worst case. But yeah. All right, moving on to Gigigol's solution. So Gigigol does something quite different. And we'll see this idea come back later. But Gigigol's idea. Okay, so well, let's see. Yeah, we'll start with this reactor. So Gigigol takes sort of prints out this big block and outputs it to the next reactor. And we'll see what it does with that. But is sort of a simple, quick way to do this. With, yeah, quickly inputting everything. And now, in the second reactor, Gigigol does this. So, after getting an input, you see that he takes it and, like, pulls off 2 atoms at a time. And now we can see with these 2 atoms, he sorts out. Okay, he first checks. Okay, is there a carbon amongst the or among the 2 atoms, and is there a nitrogen among the two atoms? And the reason he does this is that if you've got both of them, then you either have Cn or Nc. And what if that has 3 bonds between that? Then that's exactly the solution that you're looking for. Sorry. Just looking back at the thing. Okay, video compression is terrible. Okay. I'll have to, yeah, I'll have to look into it in the future. Okay. Anyways, so, we, yeah, so this sorts that out, and yeah, it's kind of a nice way to sort two atoms at a time. The sort of main problem with what Chichiko's doing here is because if he doesn't get both of these, then he simply throws away the atoms. So even though he's actually getting a good amount of inputs in this first reactor, half of them are going straight into the recycler. Or actually not exactly half. We'll get back to that later. But about half of the inputs are going to the recycler, which is suboptimal. It would be much better if they were all going to the output, and we'll see people who figure out how to make that happen later. But anyways, we'll return to that later. So now let's continue to Astra Nelson's. Oh wait, let me actually run this. So we see just a little bit faster, 16,600 cycles. So Astra Nelson has something that we'll see is actually decently similar, but significantly faster. So what Astra Nelson does is we have something very similar to what Greasefire did, where we pull out one atom at a time, and we use Astra Nelson uses a stick so that he can much more quickly move things to the output. So yeah, you just constantly building this out and then sorting atoms from it. And then, so we have a few other reactors that we'll see in a second, but the general idea is going to be the same as what we saw with Greasefire, where we split into the two streams and then go from there. So let's see exactly how he does that. So first, he sends nitrogen into this reactor and makes it into a stick of 4 things. And we can see this is kind of a nice quick way. The Waldos are desynced, but it's guaranteed that, well, perhaps it's timed, I'm not really sure. But at the least, no matter when exactly blue, well, I guess not at any cycle, but either way, this can desync a little bit and it doesn't break it immediately. But let's see exactly how he uses this. So Astra Nelson takes that nitrogen and then bonds in all of the carbon along as it's going forward, and then takes this input and splits it up. So we'll see that in a second. Rotates it, and then uses blue and red to output everything. It's a nice, clean, low symbol solution, just 54 symbols. No double pumping here. But we can see, yeah, we can probably guess that means that there's more to do. Alright, I'll run his solution through. We're now down to 12,000 cycles. Yeah, I think, well, let's see. Yeah, you're right. Because even if it doesn't get the nitrogen, that just means it would not complete a loop. So yes, that is synced. Thank you for correcting me, oh buddy. Okay. All right. Let's see. Let's now go on to Britboy's solution. So Britboy again does something quite similar. Where yes, it's actually very similar, but sort of just more efficiently overall. So first off, it does this sort, just very similar to the way we saw before. And the other reactor He does it instead of using multiple reactors in between, uses one reactor to um, merge the two things. So it's just kind of a faster version of things we've already seen. I think I'll take a moment to actually discuss. Well, let's actually take a step back and look at kind of some of the general like approaches we've seen so far. Because I think this will be like good perspective for what's going on, and also I can give a little insight into like a thing some thoughts on like the puzzle design here. So the first algorithm we've seen is like you take like split one atom at a time, or yeah, split atoms into two streams. Um, and uh, we saw um, Gigigal's solution of take two atoms at a time and sort out. See, but yeah, and we'll see kind of both these ideas come back a lot later on. I think another interesting thing is noting how people are using the reactors at the moment. So we can see that let's see. Yeah, so we've seen actually most of the solutions so far. Let me also run this through. We can see most of the solutions. Actually, have just used two reactors so far. Astro Nelson's didn't, but it's also probably possible. Yeah, he could have used something like Burfoy's design to do it in two reactors. So I think it's worth noting, you know, why are people using two reactor or yeah, more reactors probably means that you can make it faster, right? So what's with all the two reactor solutions? And I think the big thing is it's kind of hard exactly to know where to go in terms of improving this. So first off, it's worth noting why is the reactor limit 5? This was specifically chosen because like if you have like okay, the idea that like immediately came to my mind when I was trying to create this puzzle was that you could do something kind of like I'll just sort of draw it out and explain exactly what I mean. But if you have 6 reactors, then you can have like the first data reactor like split everything then have this be exactly our first idea. So have this or sorry, not split everything. Make like 2 big blocks. So like I don't know, or you know, somehow send I guess split input stream, yeah. It's kind of the best way to describe it. Somehow split up the input and like send it to each side, and then have like each of these do the same thing, and then merge the output. And this is kind of like my immediate idea for how you would do this. And I think, yeah, I was hoping, I wanted to see people do something interesting. So I specifically put it to 5 reactors because either, you just have to come up with something smarter. But yeah, and we'll see other people try to do all sorts of different things with 5 reactors. But all right, let's return to SpaceChem. That's what we're doing anyways. Okay, so our next solution with 3, I believe this is also a similar thing, but even more efficient. So 3 does a similar sort of stick thing we've seen before, but everything, it's just faster. 3 does this kind of nice thing of they grab the we saw in Astronauts' solution, for instance, that he has one welder sort of pulling it out and the other grabbing from it. Whereas here, Bree notices that you can actually both while you're pulling it out or pulling out the next atom, you can remove a bond or you can move the stick to the side and also remove the bond. which allows them to sort everything a lot faster. So, yeah, this is mainly that, but faster. Let's see. And he has a really nice second reactor. So this just takes in two inputs. Um, I think, I don't know exactly to what extent this can desync, but I assume almost fully. But either way, this, because blue only gets back around to dropping, around on 6 cycles, this is guaranteed to never crash, even if there's some desync. But yeah, if at least that's if I understood it correctly. Yes. Yeah, there's the yes. Yes. So there's a bond. You'll notice red does a bond every 3 cycles. So no matter where blue is in the loop, actually, red is guaranteed to do one bond plus, while blue is in this like top section, no matter if they're desynced or not. So yeah, this is kind of a nice quick way to do this low symbol everything. But all right, let's see this run through 8,000 cycles. Getting a good bit faster. All right, now onwards to Yellow Bunny's solution. And here we're going to see the first new algorithm to what we've done so far. And I'd say this will sort of originate from what Gigi Gall was doing. So what Yellow Bunny does, so he first does this sort of stick thing, and now we'll notice we see the same sort of thing Gigi Gall did, where he sorts out for a nitrogen in either of these spots, and then a carbon in either of these spots. And if either of those is the case, he sorts it to the bottom, and otherwise he sorts it to the top. And we've got a nice 6-cycle loop for this. However, unlike Gigi Gall, Yellow Bunny is not going to throw out everything going to the top output. And instead going to sort it and turn it into outputs as well. So let's actually follow that first. So red, okay, yeah, so this is a simple sort. It takes the input, sorts it out. And we can see, again, like Astro Nelson's reactor earlier, this is always synced because this runs on a 6-cycle loop. Let's then look at this reactor. All right, so here, Yellow Bunny takes 2 inputs, and now we're going to split them up and turn them into cyanide. I think nothing of too much done. I think we'll see other people. Yeah, we'll see other people also do things with this. But all right, this reactor, I'd say this one's certainly a personal favorite. So let's see. So this is a similar. So this sort of merges the two streams of inputs basically. But how exactly? So the idea here is, okay, first off, you note that there's more, let's see. Does that matter? Yes, that does matter. Okay. Oh, no, that's fine. Okay, so important thing to note first off is, actually, let's take a second to explain why this is the case. I mentioned earlier that when you split like this, you don't actually get a 50-50 split. There 50% of the outputs do not go to the bottom. The actual ratio is 5 to 6. So let's give a quick math explanation of why. It's kind of a cool fact. Let's see. I think the easiest way to see this. So the reason is SpaceChem's input buckets. So SpaceChem has input buckets of size for this puzzle 12. And what that means is that in every 12 inputs, there are 6 carbon and 6 nitrogen. No matter, it's sort of to prevent you from getting too unlucky, and you say you get 1,000 nitrogen in a row. I mean, there's a certain point where it would make it like you would get too many inputs and it would be impossible, even if it's statistically impossible for or yeah, statistically impossible for like an amount to fully crash your puzzle. It's still it prevents things from getting too messy, and in general is useful. But in here, it actually has an interesting unintended side effect. So let's suppose, okay, you've got let's suppose that you know that your like the first atom input is carbon. Now the question to ask is, what is the probability that this is nitrogen? And the thing is, okay, if we know that the first thing in the is carbon, then since the input bucket is of size 12, there are uh, 5 carbon left in the kind of bucket and 6 nitrogen, which means that the probability that this is nitrogen is 6 out of 5 plus 6, which is 6/11ths. And you can do a similar reasoning as to why the probability is the same for other things in the bucket. So if you're looking at the third and fourth, there will be the same probability if you don't know anything about the first thing. But anyways, this will be important. This is important here, it's important later. This messes up the ratios terribly, because this is horrible. And multiple people try to come up with ways to deal with this. Alright, let's continue backwards. Back to what we were... to Yellow Bunny's solution. Alright. So, okay. Why is that important here? What this means is that there are more outputs going to the bottom. So when red is doing inputs on beta, it's always guaranteed that you know that it'll work through this back. Let's actually look at what's happening. So blue is sort of inputting these. Blue is inputting for red, and red is always inputting something from the bottom and then attempting to bond it to this thing from the top. Because the ratio is 6 to 11, you do know that you're going to be making some, there's going to be some things where you don't have like a pair on the top, and there's going to be others where you do. In general, most things are going to be like paired together, but it's not guaranteed. But all right, yeah. So either way, it's kind of a nice way. Yellow Bunny again, I believe uses. The Yellow Bunny uses this like sense here in order to like time the input for blue. It also, I believe, stays synced because of this general running on a 6th loop, which prevents it. So if blue is stalling on the input, it prevents it from being inputted a 4th time. Hopefully I understood that. Yeah, okay. I don't see any corrections from Yellow Bunny yet. All right. So let's now look at the last reactor. The Yellow Bunny takes these sort of merge stream and now uses both Waldos to separate it out and then bond it into the complete result. But yeah, altogether quite a nice solution. We'll see. Yellow Bunny says it's been a month since he made it and it doesn't know anymore. Okay, fair enough. All right, but let's continue forward. So let's let's add this also to our algorithm list. So we've got now let's move this. Okay. We're now at algorithm 3. So where, okay, now we do same as 2, but also sort CC and NN after. Okay, so let's continue forward. And first, run the yellow bunny solution through. We're at 6,000 cycles, so pretty good drop. Let's go on now to Isaac Wass. I believe, actually, I don't think I've seen Isaac Wass submit before either, so congrats for submitting this. And Isaac Wass, let's see. Yes, he does something similar to Yellow Bunny. So he runs on this 6 loop. You can see, yeah, this is actually quite similar to Yellow Bunny's, just sort of doing it vertically instead. But it's the same sort of idea at the core. Let's now see. Okay, yes. Okay, so he sends both forward. And on the top, on the bottom, I don't particularly know why he needs to do this. Yeah, I don't particularly know why he doesn't send this immediately to the next reactor. I mean, he does change the placement, but he moves it to the left, which usually doesn't really change much. But oh yeah, no, the extra arrows are, yes. There are multiple extra arrows here. I mean, you can see one right here. You can see one right. Where's the extra one in here? You can see one right here. Yeah, it's honestly an abomination. But it's okay. It's okay. Anyways, so this reactor is honestly, I particularly love this reactor. It's a really smart idea. So the thought is, okay, we're doing this. So you'll notice, in Yellow Bunny's solution, we sort out the carbon and nitrogen. So we use 2 reactors. We split the carbon and nitrogen, the C2 and N2 into 2 streams, and then we merge them together. Isaac instead does this in a single reactor. And the way he does this, so first off, okay, he does something where, well, let's just sort of watch it run. So first off, if you've got carbon and nitrogen, when you do 2 inputs, then you're sort of done, right? This gives you exactly what you want. However, so let's see, how long will this take before we get something else? Okay, I shouldn't. Okay, so now, however, when they're the same atom, Isaac takes one, and then knows that the second input is going to be different from the first. And the reasoning for this, let's see. So, okay, let's try to draw this out. I'll hopefully I can also convince myself. I think I know why, but let's see. So the idea is, okay, if you've got so let's sort of consider the situation where this fails. Importantly, we know we've got SpaceChem's input buckets, right? So we know that there's 12 carbon, or sorry, 6 nitrogen and 6 carbon coming in a batch. And we know, yeah, so there's sort of a lot of different combinations for like the 12 orderings. But we can sort of, so because of how, so first off, okay, the things that Isaac then takes from it is he takes each of these, right? And he sorts it whether it's CN, if it's NC or CN, then he's sorted that out. It goes like to one thing, and then, so the thing that we're sort of dealing with here is the CC and NN. It's first worth noting that the number of CC, like C2 and yeah, let me use that instead. Okay, the number of C2 and N2 is the same in there's the same number of them among the 6, and So this means, okay, if you've got like 2C2 and 2N2, or if you have 2C2, then you know that you have 2N2. And this is because you have to have the same amount of carbon and nitrogen, group of 12. Um, so, uh, we can sort of consider the possible situation. So let's suppose that there were 2 of these in each group. And let's say they like came in and, you've got something like this. So that means that the inputs that would come to this reactor would be first this, then this, then this, and then this. And because, and we can see that this would work. If you, if the first carbon would be fine, or yeah, so you get the first 2 carbons, then you'd, let's see, let me actually switch over to this. Okay, so you'd get the first 2 carbons, and it be split like we saw earlier, where red picks it up and moves it away, and yeah, so that would work fine. And then after going through that, it'll work. So, and you can actually kind of work through some of these combinations, and interestingly, the only thing that fails is if you have something like this. This is actually I believe the only case, and if the carbons and nitrogens are swapped. And I think it just so happens that because we're only doing 2,000 inputs in this, this exact combination never occurs. And if it did, it would actually crash. So yeah, but this is still a very cool idea. A very good idea to try to push this into one reactor. Yeah, I actually I kind of wonder if there's more that could be done with this, but I think this reactor is kind of a bit slow for some general things, but I could very much see this being used to speed up other things. It's definitely a very interesting idea, at the least. But all right, let's keep moving forward. So, all right, now he has this output of specifically 2 cyanide, and then he simply merges the 2 streams. And I'll note that this is all, that these 2 Waldos work asynchronously, and this is so that there's no, there's no interaction between them other than sometimes they both stall in the output for a cycle. And this is, this is in order to deal with that annoying ratios that I mentioned earlier. If that wasn't the case, then you could definitely do something where these are synced. But all right, let's keep moving forward. Or first run the solution through. And let's check out, yes, actually, I believe this is, only 32 cycles better than the Yellow Bunnies. And that comes from, all of that comes from just a little bit of latency. They have the same throughput, right? This is both running at 6 cycles per loop as their kind of, or I guess 3 cycles per atom as their sort of general loop. All right, now on to Dariush's solution. And Dariush does the same sort of algorithm. You can see it in action here. And yeah, it'll remind us of things we've seen so far with Isaac and Bunny so far. So he first, this reactor simply serves to move, sort of group up the input and move it further to the right. So that's used so that in the next reactor we can sort more quickly. We now, and we can also do more in this reactor. We can also bond these together in order to finish making the bonds, which other solutions sometimes had another reactor to deal with. Or at least it just added a lot to what was going on. But either way, same sort of idea of try to sort nitrogen and for both nitrogen and carbon. And then, if it's N2 or C2, split it off. So let's first see how Darius handles that. And this will be most similar to how Yellow Bunny went about this. So he sorts out the nitrogen above, the carbon below, and then from there, takes the two and bonds them together. It's all quite nice. So yeah, this is just sort of a nice timed photo. Yeah, and he uses his sensor here to make sure everything's synced. It's just a nice, simple, efficient way to make sure that if this stalls on an input, there's never much wait. Alright, let's then check out Slack's reactor, and this is pretty similar. We see Blue does this sort of trick here in order to pull more inputs to the output zone. Yeah, and the sort of the main improvement is everything's faster. Right? This reactor is, instead of being 12 cycles for 4 outputs, or I guess 4 atoms output. Now this is 10 cycles for 4 atoms output. So we're now at 2.5 cycles per atom. But all right. Yeah, this is sort of just a refined version of everything we've seen previously. So it's nice job, Darius. Also, I'll call it nice job for like completing this in like the last day. Darius cut off I think 1,000 cycles in the like last. I don't know. It was like I checked it like the day before, and that was the after I was like, okay, I'm done with my solution. I'm gonna see how people have done so far, how many submissions and whatnot. And he improved it a good bit after. But anyways, let's move forward. So now for my solution. And also congratulations, Darius, for getting 3rd place. Oh, and I should run this through. Okay, this is, yes, 5,096 cycles. So now let's move to my solution. I should say my solution is a mess. And this all kind of comes back to the 5 to 6 ratio. It really, really messed me up here. But all right, let's see. Let's see what I do. I think actually let's first outline. Yeah, let's first outline the general algorithm, and then we'll see how each of these reactors sort of does that. So let's split off to that. So the idea with my algorithm is it's sort of derived from what Yellow Bunny and like Darius did, but I do do it a bit different. So I take the first reactor is sort of like Darius's first reactor, which is like so we make a nice input. And we'll see exactly how that's done. And then it goes into a second reactor, which sorts out, specifically sorts out for CN, NC, and CC. Let me check it's not NN. Yeah, okay, actually it's NN. Okay, so specifically we sort for these, and then we split out CC. And then in the next reactor, we'll sort out like NC to one thing, and NN to another. I guess I keep switching between what I want to do. I'll stick with that for now. Then I merge these two, and I make NC, and then I merge these two. And that gives us the output. So this is sort of the general structure of my solution. So it's the same sort of idea where we're trying to sort based on the outputs of 2 atoms in a row, but I do it in sort of 2 steps. Rather than sorting both this and this at the same time, I sort out all of this from this, and then I do the second half of the sort in this reactor. Well, let's see how I implement that. Let's see. Let's switch this over. Okay. So we can see that. Let's see. what I do is, okay, I'm making something that's kind of a nice input to use, and I make these two sticks that I send to both the top and bottom output. I do it in a very weird ratio. Let's see, I send, no, it's not that weird. Okay, it's 1 to 3. So there are 3 outputs to the top for every 1 to the bottom, I think. All right. Let's see. So, what exactly? All right. So this is sort of a way of quickly getting outputs, trying to get them into a space that's nice for me, and then yeah, we'll see how I deal with it from there. So in the second reactor, I first have some stalling. This is because, so actually this reactor, okay, if you remember when I was, well, actually, let's see it run first, and it'll make sense why things are so messy here. So first I check if either of these is a nitrogen. And this is sort of the main idea of what makes this reactor fast. Instead of checking is there a carbon and is there a nitrogen, I only check is there a nitrogen. So I sort of have to do like half the checking of what other people have to do in one reactor. And it allows me to make this a lot faster. So I first check, okay, is there nitrogen? And I output if there is. And then if neither is nitrogen, then that means that both are carbon, and so I can output it to the bottom. So, sort of nice sort. And okay, why is there this delay? What I was saying that this is terrible. Why is that? You'll notice that when there's 2 carbon, I take this bottom route and do a beta input. Whereas if there is any nitrogen, I go to the top output. And the reason that this is really annoying is because of the poor ratios I mentioned earlier. Instead of being a 50-50 split where, or sorry, what you might expect okay, if there were not input buckets in SpaceChem, it was truly random, then the output ratio would be you'd send 3 outputs to the top for every 1 to the bottom. However, because that's not the case, the actual ratios are, I believe, 17 to the top for every 5 to the bottom. And that means that, and that is not aligned with this. This is doing 3 to 1. So in order to make up for that, I have to stall a little bit at the start of the puzzle, and then I have this sort of buffer that will fill as the reactor or as the puzzle goes on, while this is sort of drained from. But yeah, so I think you could probably make this reactor faster and fix this delay. The reason I didn't was honestly that the amount of possible savings from it are not that high. I think red enters here at cycle, yeah, blue's already started at cycle 92. And you know there's going to be like at least 10 cycles of delay here, no matter what. So you could save maybe 70 cycles. And I was more focused on things I saw. I don't know. That's a really optimistic. So I saw it as more helpful to focus on other parts. But anyways, okay, let's move forward. So, let's see this output. This is kind of one of the main reactors. So this reactor is going to take our 2 inputs and now split them into 2 chains. So yes, this is the second part of our sort. And yeah, it's a kind of nice, simple. Notice that we also get the triple bond in here, which is quite helpful. But yeah, it's quite simple. The biggest problem, this reactor has been the bane of my existence. So as I was mentioning, right, the ratio here is actually 17 to 5, and instead of 3 to 1. If the ratio was 3 to 1, this would be the exact right speed. It would, yeah, be perfect for this puzzle. However, because the ratio is ever so slightly, you have a little more here, this reactor is actually too slow. And that's why you see these terrible pipes here. This in order to make up for that, I simply don't I simply have this be the bottleneck. And yeah, it's kind of the most unfortunate part of my solution. I will also say I have another solution where this reactor is too fast. Um, because I need right. The problem is that that solution relies on there being constant inputs at the expected rate. And I can try, for instance, to buffer a bunch at the start of the puzzle, but that ends up actually because you have to buffer so much, it's actually slower. um, so yeah, I expect there's a better way to do this. Was very much trying to find something, but I could not, unfortunately. So this is sort of what we were left with, and is the bottleneck for my solution. Um, I think, yeah, I think if I was able to run at the rate of this, then um, I think this would have a little higher throughput than the first place solution. But obviously, I'm not. I'm just. I don't. If anyone wants to play with this, I would love to see this made faster. I do not believe that this is optimal. This is a call for people to help me. But anyways, all right, let's move forward. So, we then okay, so we've got this nitrogen and or N2 that we've now sorted out, and we're going to merge it with the C2. And this reactor was kind of freaking dirty, to be honest. The idea, this isn't really a throughput limiting reactor, so I just sort of do something that's nice for the next reactor. We're just putting them all in this big block, but you can see, yeah, I just sort of not a lot of thought was put into how to make this nice. I just sort of made something that worked. But all right, now we go to the last reactor. This one's kind of nice. So here what I do is I have red taking these inputs from over here, and blue dealing with the block from the bottom. And yeah, so I simply sort of pull everything apart. But yeah, I think I actually have no idea why the ratio. I just sort of tried ratios for blue to red until I saw something that seemed to be about right. I have not really thought about if this actually is the right ratio for blue to red, but we'll see. Like at the nearing the end of the solution, there isn't really a difference between how much is buffered between blue and red. So it seems good enough. Okay, I pass. Okay, either way, it seems to keep up fine. So I just sort of left it at that. But anyways, yeah, so that's my solution. Yeah, kind of a different algorithm than we've seen before. With trying to sort things out differently. I am also kind of curious what would happen if you, instead of sorting for any nitrogen, you sort, say, based on the left atom. So you sort for like carbon on the left and or carbon or nitrogen on the left, and then you go from there. But I don't know. I didn't end up playing with it too much. But all right. Let's now move forward to Tough Thought's first place solution. Oh yeah, I guess I should be saying names. Let's see. Let's see if there are any specifically cool names. Unnamed solution, classic, slapdash, meets everything. Rapid dimerization imminent. Okay, I don't know what to make of that. Nice. Okay, this is referencing the speed. This is a metric. Yes, it is a cycle solution. Yes, that's your throughput. Yeah, nothing really special. And then, okay, so, and then Tough Thought says here, 3 cycles per atom and plus 3 cycles per atom half sort. And Tough Thought, again, does something very different than anyone else. So let's explain what's going on with that first. So, Tough Thought, I'm going to actually return to this first diagram. What Tough Thought does is makes, okay, what we're going to see is that Tough Thought does algorithm 1. So okay, let's just erase this. Tough Thought's solution is going to look like this. Where Tough Thought does algorithm 1 at the top and algorithm 2 at the bottom. So he's going to do what GGGall did down here, but faster, of course, of course, but at the same time, do what a lot of other people did at the top. So the idea is to sort of parallelize this whole algorithm, and it is insanely fast. So let's see exactly how Tough Thought does it. So, first reactor is crazy. So what we do is we make this this sort of L and split off this these two groups of 2 from the bottom, and then just sort of the rest of it is sort of thrown into the next reactor. But yeah, I just want to point out just how this is very compact, and this is a very nice first reactor. Every single cycle, something is being, some instruction is being done, and yeah, everything. It's just very nice. The idea, I'd actually tried doing something exactly like this algorithm, where I had 2 things. Yeah, I used the same algorithm in a previous solution of mine. But I sort of I gave up on it for what I currently do because I didn't like. We'll see. As I was mentioning with the algorithm, we trash a lot of atoms here, and I thought that would be too slow. But Tough Thought just does it better, so we'll see exactly how. All right, so first off, we have this really incredible first reactor that sorts it into exactly what it's sort of just enough to do what Tough Thought needs. Let's see which side to start with. Both are great. We'll start with my favorite, this reactor. So this reactor is this it's yeah, this is just incredible. So what does Tough Thought do? So Tough Thought takes these inputs, and now, okay, if we remember let's go back to Pre's solution as a point of comparison, because Pre does something kind of similar. So Pre takes one input at a time. You sort of grab off the left, right one, and then yeah, sort of just keep going around. And he does this at 8 cycles per atom. Tough Thought does this at 6 cycles per atom. His loop is that. So how exactly does he manage to save more space? And the way is there's sort of multiple things going on here. So first off, he inputs 2 at a time, right? Because 2 are coming in at once. He also, instead of bonding and then grabbing, he bonds in a single step. So we can see, yeah, instead of having to, yeah, do that. And then, yeah, it just sort of, it very nicely works out. I think as a point of comparison, I tried to see, okay, why exactly did Tough Thought use this handle idea? Let's just see my test to sort of see, you know, why was it done the way it was. So you can see, you sort of have this problem. Yeah, there's this issue where you need, you just sort of have too many instructions that you need to do at the same time. There's the grabbing. I think things are just kind of timed wrong, and there's not enough. I think actually more importantly, there's not enough space for everything. And yeah, so Tough Thought's really incredible idea to instead use these as handles so that you can do this bond here is really brilliant. I also want to note that, okay, there, another way that Tough Thought manages to save some symbols here is he has red, and red does this minus here that serves 2 purposes. It both removes the bond for blue here, and removes the bond on red's atom. And we can see, yeah, it's just all sort of meticulously timed, where as yeah, whenever one is at the right spot, yeah, it'll work out. We can also see red does this sort of extra. It does this extra minus bond here and here, and that's specifically to get rid of this double bond in case that lasted from the previous reactor. But yeah, this is a really, really brilliant solution by Tough Thought. It does what a bunch of other people did in 2 reactors faster. And also, we haven't even gotten to the second half of it yet. So, okay, this, yeah, so we've got that, and then this reactor is sort of a nice way to merge them. We have a little delay here to make sure that there's always inputs. But here, yeah, this just sort of nicely merges everything together, pushing things into the output. It's a really nice, nice clean reactor, but nothing too crazy going on, I think. Well, obviously, I say that, but actually making this is takes a lot of iteration, and I'm sure trying a bunch of different things. But at the least, like I was able to believe that this was not too crazy to do. I'll note actually both these bond pluses are unnecessary, but sort of enough bonds happen elsewhere to where it doesn't end up mattering. But anyways, I'll leave those. Just noticed that while I was trying to figure this solution out a while ago. But anyways, okay, so that gets us through the first half. Let's see now the second half, which is this. So this sort of elbow. So how does this work? It's sort of a okay. Yeah. So we do sort of what Chichigo did, where we pull off 2 of these things at once, and then sort based on whether it's 1C or nothing. And yeah, it's just done very nicely, very compactly, or yeah, it's quite compact. And yeah, it just sort of it fits the ratio right. Red sort of will stall an input sometimes because it's just a bit quicker, while blue will always get there at the exact right time. But yeah, it's this is a very nice way to do this. I had something in my algorithm of this. I had something similar. I think it was slightly slower, but yeah, as a comparison. Yeah, this is very nice for such a random input. Yeah, it's very impressive what Tough Thought managed to do with this whole scheme of like pulling off 2 at once here and this 4 here. And the fact that everything is like both these reactors are running at an instruction every single cycle, which is just it's very incredible. It's worth noting that there is a little lost here because, like with Jujiko's solution, where we are throwing out a significant amount of outputs. But this is sort of necessary because we need to do this all in one reactor. The only way you could do something comparable is like with Isaac's solution, where he tried to do, where he came up with sort of a different way to manage this. And Tough Thought actually shows we'll actually see he does something different in a fun solution, but it turns out to be too slow. But all right, now we merge the 2 input streams. Let's see. So first off, there's a sort of interesting thing with red will start by doing the bottom row, and I think this is mainly because red and blue sort of work in sync. Red has some, I believe the minus bond here also goes for blue. And so because the top input starts later, blue sort of needs to wait, and the Tough Thought noted that it was more simple efficient to simply have red do the loop for the starting bit and do it slower. But all right, so now because this whole system is 6 cycles per atom, or sorry, 3 cycles per atom, which gives us to 6 cycles per output here. This is running at the exact right ratio. Um, and we'll notice it never stalls because we waited for this reactor to always be running with this delay. So red will always be running, and this minus one is always timed because of the fact that this reactor always runs on 6 cycles per. Or there's always 6 cycles between outputs, I believe, which allows, um, yeah, allows this to always be timed properly with this minus one here. But yeah, this is a really excellent solution by Tough Thought. Definitely congratulations on first place. Yeah, this is a very incredible solution. Uh, I think I tried something similar at one point and was nowhere close to so many of the optimizations in this solution. So, very incredible job. All right, let's now take a look at the next some of the other solutions. So, or some of the fun solutions. So, Yellow Bunny. I guess first off, we'll see. We had 2 people submit symbol solutions. Isaac unfortunately had the worst symbol solution. So Isaac does this kind of actually. It's actually a pretty cool idea. But unfortunately, it's a little too slow. Or sorry, uses too many symbols. It's just PGGO's solution, but symbol optimized. So uh, sorts out sort of sorts both at once. And yeah, it's quite nice. Unfortunately too slow. But all right, let's run that through, and we'll see. I think this reminds me of I can't remember which puzzle it is, but there's a I'll pull it up in a second actually. But um yeah, this is sort of a there's another puzzle that has a solution almost exactly like this. Um, where the idea is you wait until you get nitrogen and pick that up, and then once you get carbon, you bond that in, and then make an output with it. It's works pretty well, and everything else that doesn't get sorted goes straight to the recycler. Yeah, let's see if I can find it. Do I have... no. Okay. It's this... No, I don't have it here. Wait, no. Here... No ordinary headache. Yes, okay. Okay. This is a less optimized version of it, but either way, it's a similar idea where you like grab an input and then bond in the other when you're done. Either way, this is a less optimized version of exactly what the record does, but it's a similar version. Anyways, just reminded me of that. Okay, and let's see what other people. Of course, we have Yellow Bunny with his single Waldo solutions. Well, first, since we're in the looking at symbols, we'll first take a look at symbols. Oh, this solution is actually quite cool. So essentially, um, uh, Yellow Bunny is making a stack out of these. So you'll notice that, okay, in this situation where he, let's see, let's get it to loop for a little. Okay, it doesn't want to. So we'll notice when it loops, it just sort of bonds everything down. And yeah, so we're essentially making a stack. And once there's both nitrogen and carbon, we pull from the top of the stack, and then sort of iterate through. But yeah, that's sort of the, I guess, CS way to say it. But either way, essentially, yeah, we've got the storage and we're constantly pushing and pulling from it, and trying to, yeah, make outputs from it. Yeah, it's a very cool way to do symbol optimize this. So very nice. Let's see. All right. So then we have, right, looks like Okay. We then, okay, so this reactor, so this is a or cycle optimized single reactor. And Yellow Bunny does something kind of similar to what we've seen with other people, but obviously has to be slower, being one reactor or one Waldo. Um, so we've got a nitrogen and carbon outputs, and then we sort of merge together, sort of similar to some of the other first solutions we saw, but a little slower. Yeah, and that runs 60,000 cycles. All right, and then we have, yes, so then we have, I think, and then Greasefire also tried Jujigol's solution, a very similar type of that. But I think his implementation of it was a little slower. But either way, nice job for trying that idea. Yeah, I'd actually, yeah, when I decided to do 4 sensors in this, I had the idea in mind that one could sort 2 atoms at once. The way I was thinking you would do it was very different than I ended up doing it and how other people did it. But it was still uh, yeah, that idea had been in mind when I had done this, and I was hopeful to see how people would use it. And clearly, people did use it in very cool ways. So, yeah, I'm quite happy with how the puzzle turned out. It seems like there were a lot of different things to do in this puzzle. There wasn't really an obvious, as we saw. I mean, both my I didn't even run this to. Wow, okay, what am I doing? All right. Let's actually run this through and see the actual cycle count. So it's 3,900, which is about 170 cycles faster than my solution. Or yeah, and then yeah. So, but yeah, I think it was very nice. Like me and Tough Thought had entirely different approaches, and we were still very close. So it's cool seeing that. But yeah, and then Tough Thought shares Double Q, which is it looks like it's a similar solution to what he ends up doing, but he does something sort of more interesting in this top reactor in order the reactor with the recycler output. So what Tough Thought ends up doing is, so first off, if he gets CN as before, he simply outputs it. But if he gets N to NN or N2 or C2, he does something a little different. Instead of immediately throwing it out, he'll attempt to push it into this sort of queue as he's stated it. And if there's both, when the next thing comes by, if there's both nitrogen and carbon there, then he outputs it. It's kind of it's a cool way to go about this. Unfortunately, my guess as to why this wasn't better is that this reactor is just not dealing with as many outputs. Just sort of you're dealing with half the inputs and trying to sort them more efficiently. And he's just not able to get a lot out of it. If he was able to fully sort everything and not, so the thing is, if say two C2 come in a row, then the first thing will just be thrown away, and that's obviously not optimal. So some things are still being put in the recycler, and there's also the fact that I think like the majority of things are still getting sorted. But the other problem is this last reactor. My guess is, so we'll see it once things start showing up. But, oh wait, actually, let's actually look at this reactor first. So this is, okay, yeah, so this is a similar thing. Yeah, this takes the output from the reactor we've already seen. Yeah, so to make this clear, we go from this reactor to this reactor. So we've already seen. This is probably an older version of what Tough Thought submitted in his final solution. And then here, yeah, so he starts on the top. But we'll notice here, so this is the output from this reactor. When he gets two things, it's sort of too hard for him to turn both of them into the output. And so he actually has to throw away half of it, unfortunately. But but yeah, it turns out actually this block of like N2C2 is actually really annoying to process. There's like a yeah, it is there's a reason like Darius, for instance, used two reactors to deal with this sort of thing all together. It's quite annoying. um, but either way, yeah, it's sort of a interesting approach by Tough Thought. But all right. Oh, whoops. All right. So I think that covers all the solutions for this puzzle. So let's now announce the next puzzle for the November monthly puzzle. So the puzzle the for November will be mind the input delay. Tough Thought was the only person to submit a solution this month, and he submitted the same puzzle he submitted last month. So it is the puzzle we will be playing. So if I will request please please someone please try making puzzles for next month. I don't think I will personally be trying to make one. It would be yeah, it definitely it would be unfortunate if we have no puzzle for next month. So start thinking about it, I guess. But all right, let's explain what's going on in this puzzle. There are two. Oh, I have something there. Okay. So there are two. Let's see, two sort of inputs. And as in the title of the puzzle, the thing to notice immediately is that the input delay in the top, which is the distance between these inputs, is 1 cycle, so they're coming every cycle, whereas on the bottom, it comes every 10 cycles. So you've sort of got these differing speed inputs to try to manage, and also you have these pointers or pass-through counters in the middle. All these do is they make sure that you pass the exact inputs given to the following reactor. So essentially, you have to come up with some way, some sort of way to manage this. And like with Cyanide Factory, the metric is cycles. The goal is just to be as fast as you can. But yeah, let's see if there's anything else to note. Each reactor is 8 bonders and 1 sensor. And 40 outputs on each. So, all right. I think that concludes our stream. I will release the round for this. I'll throw the export in the channel now. Just so nobody has to go looking for it. Actually, wait, I don't have it. I don't have it right offhand. Okay, I'll do that. I'll do that after the stream ends. But yes, so that'll be the puzzle for next month. All right. Well, I guess anybody have anything they want to say, point out, questions about design choices? I don't know. Not seeing anything in particular, I guess. So yeah, I guess thank you all for coming by. Yeah, this was very fun. I'm glad people. It was cool seeing the solutions for this. Yeah, no problem. It's kind of fun going through all the solutions and trying to explain what's going on. Because there's a lot of things, like even if you do like even if you have like a really good solution in one algorithm, you might like not really understand one thing that's important for another or something. I know it was a while before I looked at it was funny actually. The noticing like the input ratio thing, I think I was immediately like I think the input buckets will affect this, and so I was like, okay, I'll just like write a program to check like what the thing is, because then I'll just know exactly what the ratio is. And I wrote it wrong, and so I got that the ratio was like 1 to 1, and I was like, oh, okay, well that was I was kind of expecting it to be weirder, but um, I guess it's not. And then I kept running into like weird behaviors, and I went back and was like, oh, let me check over my code, and it was like very wrong. But anyways, we got there eventually. And then there's the like easy probability way to like kind of describe what's going on. But anyways, um, all right. Well, thank you all for coming by. I'll try to upload the recording so people who didn't come see that. I guess I'll stop the recording here.